I've been on the railway just over 20 years. I'm an incorporated engineer registered through the PWI. I've been on high speed for about 2.5 years now, as a senior asset engineer, starting off in the technical authority, then after a bit of a reorg into the asset management side of it. So that is the long and the short of it, really. I've done all sorts of things across the railway, from section manager to ATME to route asset engineer to asset engineer, etc., etc. So yeah, just as I say, most people know me anyway. So.
Thank you, Mark. Sorry, I'm having a small issue because I've only got one screen and I'm sharing it, which means I can't see my presenter notes. So I'm going to wing it. So to give you first of all, a brief overview of who we are as Network Rail High Speed. So we operate, maintain and renew the high speed infrastructure on behalf of HS1 Limited, who have a concession to own and operate the infrastructure from the UK government for a 30-year period. So although we wear Network Rail vests, we are a limited company in our own right, and have our own organisational structure, employing around 500 people. The assets that we look after is the little bit of France that stretches into the UK. So initially, Eurotunnel opened as the rail connection back in 1990, and initially that just took trains into Dollond's Moor and off onto the conventional network. So in 2003, almost 20 years ago, believe it or not, from our new railway, Section 1 opened. So this provided a high-speed connection at 300 kilometres an hour up through Ashford and the Medway towns, and then connected onto a section of the conventional network into Waterloo. So we, at that point, we were using dual electrified Eurostars that went onto the rail network. In 2007, we opened what's known as Section 2, and this connected us under the Thames and into our new terminal at St Pancras. As you can see from the dotted areas here, we have 3 long slab track tunnels as part of Section 2. So these are single bore tunnels travelling at 230 kilometres an hour. We are TSI compliant infrastructure and gauge cleared to UIC GC on the main route, and GB1 on the connections to the conventional network at Ebbsfleet and Ashford. So we can essentially take anything Europe can throw at us, taking goods via Rainham and via Dollond's Moor, and taking passengers into the UK via St Pancras. Before we talk about track, it's worth mentioning trains. They're a fairly integral part of the system. So we have 3 main classes of passenger train, these being the original Eurostar Class 373s that have operated on the network since day one and are effectively Thales LGV stock. We then, when Section 2 opened in 2007, brought on the domestic Class 395 Javelin units. So these are only able to do 230 kilometres an hour and bring some interesting compromises with them, in that they then have to go onto the domestic third rail network and trundle round Kent at up to 90 miles an hour from memory. So much softer suspension characteristics, different wheel profiles, different dynamic behaviour. To then further widen that gap, in 2015, we brought online the Class 374 Volaro units. So a more modern design than the 373s, but from an objective point of view as a passenger, probably not as nice to ride on as the 373s, and from experience so far, probably not as track friendly. But these are similar to the 373s, capable of running at 300 kilometers an hour on our infrastructure. And similarly are a 16 car unit with axle loads up to about 16.5 tons. We are also open to freight. So as a couple of examples of the type of locos in use on the infrastructure, in the middle is the Krupp locomotive used by Eurotunnel. So we use these for a lot of our engineering movements. The original ones were diesel powered. They've recently started to convert to battery units, and they're initially designed as a rescue train, so capable of hauling out a Eurostar, but we use them for dragging around various types of yellow plant. And similarly, the Class 92 locomotives are capable of running on our overhead system. The reason that we are limited in the types of locomotive we use, Mark will explain later, but is down to our signalling system. So today's presentation, I think I've bought a few PWI sessions talking about high-speed track, as did my predecessor. So I thought it'd be interesting to take a bit of inspiration from Peter's talk last month, and to think more about our infrastructure as a whole rather than just the track element of the system. We're often asked on high speed why we perform differently to the rest of the UK network, and why we're able to set the performance targets and availability targets that we do, and that doesn't happen by accident. In both a good and a bad way, a lot of what we do today was set in place 20 or more years ago when the infrastructure was designed and constructed. So what we'd like to do today is to explore those connections within the system, and how they influence in various ways our approach to maintenance of the assets. So I'd now like to hand over to Mark to talk through some of that detail.
Thank you, Matt. So the fundamental part of our infrastructure obviously is the track, and a little bit like me, it's very simple. It consists of rail, sleepers and ballast. Rail essentially is exactly the same as the RT60 rail you use on the conventional railway, although the difference has been with our sleeper design. We use twin block sleepers, which give us a greater adjustability, stability, and geometry, along with a much bigger footprint. So the load bearing, it gives us a larger load bearing area and reduces our geometry issues. Combined with tight sleeper spacing, provides a better support for the trains, minimises deterioration, and therefore we have fewer issues with things like twists, and specifically cyclic top, which isn't really a thing on our railway, fortunately. Ballast specification is at the higher end for what you'd experience on conventional lines. We have LA rating of 5 and an MDO of 14, so it's exceptionally hard, and we're now seeing how the hardness and resistance to attrition has become quite important to our infrastructure with our train capacity. Can you on to the next one, Matt?
Yeah.
So our rate of deterioration is linked to the quality of the support system. So you know what's stopping the train from falling into the ballast. Our formation design is a big advantage over the conventional track bed, especially around the Kent and Sussex area, where a lot of the conventional stuff is either ash or it's built on clay, which causes a lot of issues. We're essentially built on an aggregate layer, so essentially our track is built on a road. So a lot of our issues, a lot of the conventional issues don't exist on our railway. This gives us better consistency of support and stiffness, resilience to formation mixing with the under sub base, and that's not really experienced anywhere else on the network. So consequently, we don't get pumping of the sub base up through the ballast. So wet beds are a thing that we don't suffer with, fortunately. Drainage, obviously keeping the water out of the system, and it enables, because we have such good drainage, it reduces the rate of our ballast attrition. Our drainage system is probably the most modern in the country, with the exception of maybe HS2 when it eventually comes online. But we have exceptionally good track quality because of our design. So structure interfaces are a little bit more interesting. They provide us with lots of geometry issues. So because our drainage is built into all of our underbridges, so it's a little bit more labour intensive than it is on the open route. Some structures drain well, and some drain when they shouldn't. So it's keeping on top of our tunnels and etc. It can be a challenge for our civils teams. We have to manage changes in stiffness on the runoff and runoff of the concrete structures. So going from standard track bed to the tunnel and our floating track slabs. We have to manage the stiffness on other structures, such as some of the viaducts. We have rubber boots used on the slab track, try and manage the stiffness issues going from one to the other. And some of our structures breathe, which leads to ballast migration discontinuities in running surfaces. So they're specifically around the viaducts, really, midway viaducts, which means we have expansion joints below track level, and that again creates challenges with inspection and maintenance of civil assets. With our access probably as limited, if not more so, than the conventional railway, all of our maintenance activities are a challenge. Next one, please, Matt. So, as well as environmental benefits, overhead electrified railways mean we have lighter trains, better traction characteristics, and is a little bit more track friendly. Although, as Matt has already said, the newer Velarios are proving to be a little bit difficult when we get into our low speed areas around St Pancras. We have a 5.1 metre contact wire height, which enables our staff to be on track without having to provide isolations during our possessions. This gives them a safer working environment. However, it does mean the effects of track lifts and sloughs in relation to the pantographs and the wire height are a bit of an issue when it comes to tamping. And we're also facing a bit of a challenge in that we've got our ballast cleaning campaign coming up, and that's proving a bit of an issue. It's auto tensioned with the contact catenary controlled independently. So the tension is provided by counterweights on the back of the wires. So they're always under a constant tension. The tolerance range for the contact wire position is about 40 millimeters. So again, when it comes to tamping, etc., it does cause a bit of an issue. It does help the fact that we've got managed track position, and we tamp to design and use dynamic track stabilizers to consolidate the position. But with just a 40 millimeter tolerance, it does become a bit of an issue. Next one, Matt, please. So all of our command services are in one place, and that makes communication easier and allegedly simpler. Sometimes it's not always the case. We do have issues now and again, but generally our communications and signalling is fairly good. We use in-cab signalling on the high-speed sections of the route. TVM 430 is our signalling system, and it means we have a lot less trackside furniture and a lot less cables, and drivers can sit back and relax a little bit on our high-speed sections. We have no heavy-duty signalling gantries because of this, so the environment isn't as impacted as it would be on a general overhead catenary system and a conventional signalling system. We do have lots of loops and cables in the forefoot, which again, as I'm sure that of those of you who have been on the conventional network, does cause a few issues when it comes to tamping, and we have had a couple of cable strikes which have caused us a few issues, but it hasn't been something of a major issue. As long as people are aware of them, we usually get around it. Renewals and ballast cleaning is a bit of an issue when it comes to the signalling system, because we have in-track beacons for the TVM 430 and the cables and loops and all the other stuff, good stuff that goes with that. Planning for our ballast renewal is proving interesting, and it's caused a few, shall we say, heated discussions with our signalling colleagues to establish, what they can do in the proposed possession times that we're looking to do this ballast cleaning. However, speed restrictions become a lot easier because everything's done remotely and everything is done as a preset speed. So we don't have boards on track, we don't have metal Mickeys that fail, we don't have to put people out on the track and impose lower speed restrictions while that stuff's going out. So everything's controlled from our control centre in Ashford. Possessions are taken via ERS switches, similar to a lockout device. This enables us to take protection and apply it remotely without staff actually entering the danger zone. We, as a point, operate a permanent green zone whenever our staff's on track. No one is allowed on track red zone, and that is a golden rule of our system. It does impose limitations on possession lengths with the ERS switches and lock, etc. And we still need to operate things manually. So, yeah, although we don't have the issues of TPWSs and in-track magnets, etc., etc., it's not the be-all and end-all. There are still limitations. Next one, Matt, please. So our high-speed switches and crossings are capable of 160 kilometres an hour with moves of through routes of 300 kilometres an hour. They provide, you get, as you can see from the picture, you get a clear continuous running surface, minimising impact forces, and that maximises our ride comfort and longevity of the asset. As our concrete bearers are fairly tightly spaced in comparison to the rest of the network, this gives us an excellent but very stiff support conditions, but it does prove that we get it does help with our ride and track quality issues. Units have to be long, so typically we're looking at a transition of a 90 meter toe to nose and 3,000 meter turnout. So this enables high speed, comfortable turnouts without people spilling their coffee. And I'm told, actually, if you go over to you can actually notice the difference when you go from our side to the French side. Not because their switches are any different, but ours are just a little bit better maintained. Switches and crosses, the only place we need insulated rail joints in the TVM, but these are only needed on the crossover side. It just isolates the up from the down. Motors and supplementary drive equipment are mounted directly to the layout, so that removes the need for additional support. And most of our cables are conveniently hidden below the ballast in cable routes and under track crossings. So yeah, if we could move on to the next one, Matt, please. So if we take trains out of our system, which would be great because it'd make our life a lot easier. But we can't. So we have 16 cars, 16.5 ton axle loads and 300 km/h running. And that has a big impact on our system. It means that while we don't have to maintain them often, when we do, things are a bit of an issue. So because we attempt to design using heavy duty machines, we also carry out track dynamic stabilization and ballast regulation to consolidate the track to get us up to line speed. However, through our switches and our crossings, because everything is so stiff, we do find that we are having issues with ancillary equipment, as in the motor bearers, not the bearers themselves, but the bracketry that hold the motors to the bearers. I don't know if you can see in that picture, you've got a motor sitting on an angled bracket which is bolted to the bearer, and what we're finding is, or what we think we're finding, is resonance from the train wheel or the train going through the crossing isn't actually causing voiding, but it is causing harmonization issues with the bracket, and the bracket's failing because it appears that it comes with the perfect gives it the perfect harmonics to induce metal fatigue within the bracket, which causes the motor to bounce, which causes the cables to break inside the motor. And at £10,000 per motor, it's not something we really want to happen very often. So we're working on that issue at the moment. Traits on the overhead line position and difficulty in providing adjustment across our track interval limits, lifts and slews mean each tamp's less effective at restoring the design, and therefore we have to do it more often. Presence of stretcher bars and point operating equipment for the MCM Type 91 motors prevent us from tamping the most sensitive areas, so we rely on our track maintenance teams to go in and road bell through those areas. That has been a bit of a learning curve for our guys, because it wasn't something until recently they've had to do, but we're getting on top of it, and yeah, they're doing a good job. So because our track is so stiff, where we have cable routes and UTXs, this can highlight issues with geometry. Again, this is something we're only recently starting to encounter. Some of our UTXs are causing the ballast above them to deteriorate, and we're getting isolated geometry issues, which we're having to deal with. And while our design allows for the two roads to be maintained independently, this does lead to issues with differential levels if we don't tightly control it. So essentially what we're trying to do is probably move in the direction of tandem tamping to ensure that our S&C units remain parallel and level with each other. The last thing we need is one track starting to elevate above the other. And so, as I said before, where we can't tightly control the forces, they get transferred into the system, elsewhere into the system, i.e. the point motors and the bracketry on the end of the bearers. And that is probably one of our biggest issues at the moment. And I believe that is where I hand back to Matt.
Thanks very much, Mark. This presentation could have been anything from 20 minutes to 2 hours. So hopefully we've given a bit of an overview of some of the good things about our asset and the challenges that we face. There's lots more that we could discuss around the access regime, possession, delivery, and challenges of getting things into the middle of a 7-kilometre single bore tunnel. But perhaps that's one for another day. To summarise, this is railway engineering, not rocket science, and nothing that we do is particularly unique or out there. We have the benefit of a smaller network and more sort of closely controlled conditions than I've probably experienced elsewhere, which means that we're much more able to drill down to root causes and to better understand our asset behaviour. We also have the benefit of a well-designed asset and having those baked-in benefits of not having to worry about formation and drainage, of being able to separate people from trains more readily, and having a system that maximizes the intervals between maintenance by supporting that level of high performance does make our life easier. It is important, however, that maintainability is sort of baked in at the design stage, and a lot of the issues that we see were probably foreseeable, and what were good construction decisions haven't necessarily supported an easily maintainable asset. So it's certainly one of the big lessons I feel that new can be learned on new construction is that those requirements need to be at the forefront of your thinking, right from sort of conception of the route, even down to the position of access gates and getting equipment on the track. As engineers, one of our responsibilities is to find the least worst option, and in a multidiscipline scenario, that compromise is really important, and understanding the performance needs of our individual assets and making sure that we find a balance that is deliverable for everyone, even if no one's absolutely thrilled with the output, represents really good sort of interdisciplinary maintenance. And I think that's something that we've developed really well, particularly around our switching crossing assets, to have a much more collaborative approach to root cause analysis and to problem solving. There is, however, always room for improvement, and we to some extent are playing catch up on asset data and asset knowledge. Systems and IT as ever have moved much faster than the railway does. and we're now trying to fill in some of those data gaps that allow us to better understand our trends in condition and asset behaviour. Having access to that information will be critical in the future in allowing us to become more predictive and less reactive in how we approach our asset maintenance, and particularly in optimizing things like our tamping intervals, so that we don't allow assets to get into a degraded state, but also that we don't unnecessarily degrade them artificially through maintenance activities. So our future approach to remote condition monitoring, data capture and analysis will allow us to greatly improve our understanding and increase our ability to make informed maintenance and renewal decisions to sustain a high performing asset in the future. Thank you very much for listening, and if you have any questions, me and Mark will be happy to try and answer them.
Thank you for that, Matt. Thank you, Mark. A number of us were quite keen to hear a bit about your presentation today, because as a section, we had a presentation from the guys at Eurotunnel. I think it was last June, May, June time. So this was the bit that kind of pulled it all together. There is a couple of questions in the chat. Before I get to that, though, I've got a couple of questions. One with regard to the twin block or the dual block sleeper, and one about the slab track in phase 2. So with the sleeper, why was the twin block sleeper decided upon? Was it a European system or solution that had been tried and tested on high-speed rail elsewhere? And with regard to the slab track, with those 3 independent locations, was it the same system base plate holding down bolts that were used on all 3? So sort of two topics there.
So the sort of reference system for our asset is the LGV Mediterranean. So it is based on SNCF components and design. There are 2 or 3 key advantages of a twin block sleeper. One is that the flexibility of the bar makes it easier to maintain geometry and to maintain the rails independently, which when we're looking at intervention limits for twist of 7 millimeters, it's really important to have that degree of freedom and that ease of maintenance. It takes away the risk of becoming centre bound and of sleeper failure. And probably the biggest benefit, so if you notice, the shape of the block is actually trapezoidal, so you've got a really big contact patch with your bottom ballast. So in terms of the track fixity and the associated sort of lateral resistance in hot weather, they're a really stable system. And that's been reflected in our seasonal performance over the last couple of years.
Very good.
Moving on to the slab track. So the system in all 3 tunnels is the same, except for some changes to pads to manage stiffness on the transitions. Our slab track design is actually the plain line system, so the twin block sleepers and the same rail embedded into the slab with a rubber boot used to isolate the vibrations. So it's not a direct fastened slab similar to a lot of others.
Gotcha. Okay, well, thank you for that. Phil, I see you've got a couple of questions. Do you want to have a word with the guys about these?
Yeah, sure. Yeah. Hi, Mark. Hi, Matt. Thanks very much for your talk. It's very interesting. The first question is: has there been a notable increase in track maintenance, particularly with maintenance of track geometry, since the introduction of freight traffic?
So not really, because freight traffic accounts for a very small percentage of our total traffic, so it's only around 2% of our traffic volume. I did a little bit of analysis a year or so ago to see if we were seeing, my theory was that we'd be seeing a lot more sort of imbalanced forces on the low rail, particularly in the high can curves. But there is no evidence to support any sort of increase in low rail issues, even since we started to run heavier axle loads. So the reason for that analysis was we increased axle loads up to 22.5 tons for refrigerated carriages to keep everybody fed during COVID. So so the short answer to your question, Phil, is no, not really.
Okay, that's interesting. Okay, thanks very much. The other one is there a program of rail replacement after up to 20 years service? And are HS1 NR considering an increase to the stress-free temperature for newly installed rails due to climate change predictions?
So I'll answer the second part first. That one's a little bit easier. So we have been looking into the resilience of the track system and the sort of future forecast temperatures. At the moment, there's no evidence that an increase in stress-free temperature would be beneficial. There's so nothing to suggest it'd be particularly detrimental, but we're not currently looking to change our SFT. We are, however, looking at more detailed analysis of the interaction between the sleepers and ballast, combined with the lateral resistance provided by the rails to understand the contribution of each element of the system. And if we were to make a change to that design to increase climate resilience, would stress-free temperature be the right thing to adjust, or would a change in the ballast profile or sleeper spacing, for example, provide a greater benefit?
Yeah, no. Yeah, sorry. Yeah, I'll get that. Thanks. Yeah, I mean, of course, increasing it because the air temperatures forecast to change in the future means looking at the cold end as well, doesn't it? So looking at the stresses in the tensile stress on a cold winter's night. So yeah, I'll get that. Anyway, thanks very much.
Yeah.
Yep, cheers.
In terms of rail replacement, we've seen some really encouraging results. So yes, at around 20 years, we were expecting to be replacing rails. What we found when we went to validate the re-railing program is that actually the wear rates are a lot lower than we were expecting. We don't think that's by luck. We think it's a result of the construction methods. And I've also normalised that against traffic to understand how many tons of traffic that equates to, rather than just a number in years. So we've probably seen a little less tonnage over that 20 years than the system was designed for. We've kind of taken a snapshot in time, and what we'll now do is continue to iterate on that and gather more information over the next few years to validate those assumptions of rail life. But yeah, at this point it's encouraging, and it's only the sort of localized problem areas that are driving rail replacement, rather than any need to do wholesale changing.
Yeah. Do you think your rail grinding program has also contributed to that? You probably do more rail grinding than NR per mile, if you know what I mean. So yeah,
we do. Yeah. Similar to the tamping, having the luxury of taking a preventative approach has made a huge difference to the asset performance. So we follow the best practice that's laid out in a way that most TME areas don't have the opportunity to. And we do grind to remove that damage layer before we start getting cracks propagating. So that's undoubtedly contributed to the performance.
Yeah. Okay. Thanks a lot, Matt. Cheers. Somebody else can have a go.
Yeah.
So,
Howard, you had a couple of questions for Matt and Mark?
Yeah, one was in the 20 years that it's been going, have you changed any of the swing nose crossings?
Yes. Yeah, we've
go on,
changed a
Mark, you
couple.
take this one.
Yeah, we've changed 2 or 3, and it has been a bit of a challenge. As Matt alluded to earlier, the construction of our railway is great, but it hasn't really been designed for maintenance. So we've had some big issues in replacing some of the crossings, and to the point where we've had to bring in the Kirov to replace them. We are looking at using panel lifters and alternative methods to get them in and out. But yes, we have essentially is the answer to your question.
Thank you ever so much.
Howard, you had a second question.
Well, just looking at the dates, was you given a 30-year contract on the railway?
No. Short answer. So HS1 have the concession to own and operate, but we as the maintenance contractor we're on a shorter time frame. I don't want to say what the current one is because I can't remember off the top of my head, and I don't want to get it wrong. But we do have we did extend that relationship fairly recently, which I believe is for a period of about 10 years.
Right.
But as I say, I don't want to upset anyone in either side's legal team if I've got that horribly wrong.
Lovely. Okay, thank you.
Peter Alford has asked a question: are you sharing the lessons learnt from maintaining HS1 with HS2?
It's kind of funny you should say that, because I'm currently at Birmingham University doing a master's degree in engineering, in railway systems engineering, and HS1 is very rarely mentioned. HS2 is mentioned a lot, but I have to sit there and remind them that we do actually have the only high-speed railway in operation at the moment. As far as I'm aware, we've not been approached by HS2 for any kind of lessons learned, and I have I've seen reports where people working on HS2 are saying, oh, we did this and we did that and we did the other, and I'm sitting there thinking, well, why didn't you actually come to us in the first place? We could have done that for you and saved you a lot of legwork. So I think essentially the answer is no, we're not being asked.
Particularly if you've got problems with access.
Oh, exactly, yeah.
It sounds like they need to consider that. It's going to be a completely different animal, isn't it?
Yeah.
I can say a little bit about that. I've worked 3.5 years on HS2. Yeah, there was a couple of people from HS1 who came onto the project. Simon, I can't think of his second name. You probably know him.
Simon Morley,
yeah, Simon Morley. Sorry, yeah, yeah, senior moment there. So Simon Morley was quite a long time on HS1 and worked in the engineering directorate of HS2 and still is there, I believe. So he has brought a lot of knowledge from HS1 to HS2, and it's probably the main reason why there hasn't been a sort of a reaching out back to HS1 NR, because the knowledge has kind of come in-house. And there was also one of his supervisors as well came over. So yeah, so we did, and I personally was involved in this, and we did frequently look to HS1 to draw lessons learned. But as I say, we were able to do that through Simon, so that's probably why the reaction you gave was how it is at the moment as you see it. But okay, yeah, so I just thought I'd chip in with that. Thanks.
Bob, I don't know if you're still with us, Bob. Do you want to ask your question?
Yeah, a really good presentation, both Matt and Mark. Thank you very much for that. Just what sort of track failures are you seeing on the route? And over the first 20 years, are you starting to see a ramp up of any particular types of failure?
Yeah, so it's been really interesting over the last couple of years that the failure trend has not been on the high speed assets. So we went through a period at about 12 to 15 years of operation where we did experience some failures on the high speed sections, and it sort of brought about a step change in maintenance capability. And probably the biggest issue on the high speed section is probably ballast pitting that you don't see elsewhere, but it doesn't tend to lead to failure. It be managed by grinding and defect removal. Swing nose crossings and defects in the reduced section of the high speed switches, squat type defects, and RCF between the point and splice of the mobile point, so it's just 260 grade rail, are probably the biggest drivers for sort of maintenance and defect led intervention. In terms of service affecting failures, though, it has been crack crossings, a lot of IBJ related failures in the St Pancras area, particularly around the hot weather period, which was frustrating because it feels like something we could have managed out. When I say a lot, we had 3 over the course of the summer, but they were our big contributors to performance. And our most recent failure last week was due to a welding process failure. The crucible failed, leaving us with a sort of incorrectly formed welding track. So it has been the high speed infrastructure itself has been very resilient in terms of direct impact on performance.
Thank you.
Good. Well, look, I don't see any other questions, so I'd like to hand over to Phil. Phil, do you want to do the vote of thanks for Matt and Mark?
Yeah, sure. Okay, thank you. Thanks very much, Matt and Mark. Big respect to you guys looking after our highest speed railway in the country. It carries a lot of responsibility, and you've got to react to things a lot quicker than the conventional network. So I think we should salute you guys looking after this railway. It's a difficult job and a very responsible job, and great presentation. Enjoyed going through it again, having worked on a CTRL in the construction days myself. It's good to be reminded of that myself, and some good questions as well, and you've really answered them well. So thanks a lot. Thanks for spending the time with us at the Ashford section. It's much appreciated. Maybe we can have a site visit one day to HS1.